Let's talk about reflections of graphs and how to do this in Mathematica. First of all, let's consider the function f of x equals x squared plus 3x. Already got that predefined, but I need to put this into memory for Mathematica, so I hit Shift Return. So I've executed that command, and so now Mathematica knows what f of x is. Notice that the font color of f changed from blue to black. Okay, so if we have a function, if we were to graph it by hand, let's say we were living 50 years ago, we had to graph things by hand, we would construct a table of values. So we would give various values for x and then see what the output was. So like when x was -7, we plug that into the function and get 49 minus 21, which would give us 28. So you'd put in a value of x, you would evaluate the function and get a number back. And this would mean that the point -7 comma 28 is on the graph of f. And you do this for a lot of different values of f. So here I constructed a table that shows lots of different values for f. And these are all points on the graph of f. And then the next thing you would do is you take all those points and you'd plot them. And you'd get some nice plot like this. I didn't do it by hand because my handwriting is bad, but so I did it on the computer. But I plotted these points. This is what the points are, what they look like when you plot them. And then what you do is you'd connect the dots. You draw the line that goes through them, and you'd get the graph of f, a nice picture of it. I'll go ahead and do that using Mathematica. That's plot f of x, and my x values went from -7 to 5. So we'll go -7 to 5, and my plot range, I'm going to go from, say, -40 to 40. And there's the graph of f. I've connected the dots, and it's got a nice picture. Normally, in the olden days, we did this all by hand. We didn't have computers to do it for us. This is how you would do it in the computer. Well, we want to talk about how you take a graph like this, how you take this function's graph, and I want to reflect it about the x-axis. So I want to imagine folding this. Imagine this was a sheet of paper, this graph right here, and I want to fold it about the x-axis. So I want to take this part that goes above the x-axis, I want to fold it over, and it's going to come down this way. And then the part that's below the x-axis, it's going to go above it, and then the part that's above it goes below. So I want to take it and just reflect it about the x-axis. I have to visualize this in my head, how I fold this on the x-axis, as if it was a sheet of paper. So the question is, how do we do that algebraically, though? We can visualize this geometrically, and we can physically do it, but this isn't very helpful in general. Because when you draw a graph by hand and you fold it, you get these errors that creep up. So we want to do it systematically. We want to have an algebraic point of view of this, and then be able to do it on the computer. So the idea is I start with this point like -728, and I want to reflect it about the x-axis. So here's the point -7, 28. Now, if I reflect this about the x-axis, then this point is going to go from here, I'm going to reflect it, and it's going to go all the way down here to -28. I'm going to do it over here. Here, -728, this is -728, and when I reflect it, it's going to move all the way down here to -28. So it goes from, the y-coordinate goes from 28 to -28. That's what it means to reflect about the x-axis. The x value does not change. I'm still at -7. So when I take each of these points and I fold it over the x-axis, the x value does not change. The only thing that changes is the y-coordinate. And the way the y-coordinate changes is I multiply the y-coordinate by -1. Well, in the language of functions, the y-coordinate is called f of x. That's the name of the y-coordinate. We don't think in terms of y anymore. We think in terms of f of x. So all I'm doing to reflect this about the x-axis, all I'm doing is I'm multiplying the y-coordinates by -1, and the y-coordinate is called f of x. So what I'm really doing is I'm just taking the function f of x and multiplying it by -1. And so I'm going to do that minus f of x. The function is f of x. That's the y value, and I just put a minus sign in front of it. And then let's see what happens. X goes from -7. I don't change anything on the x values. And my plot range will be from -40 to 40 again. And there we see I reflected it about the x-axis. That's all I did is I multiplied the y value by -1. The x value stayed the same. I didn't manipulate the x values at all. Now, let's say I wanted to graph them together at the same time to see that these are actually reflections. So what I need to do is plot a list of functions. So I put a list in Mathematica is braces. So I have braces f of x comma minus f of x and then close the braces. So instead of plotting one function, I'm plotting two functions, and everything else stays the same. And then notice how the functions are colored differently. Mathematica takes care of that automatically. The first function is blue and the second function is red, or whatever. I guess this is red or violet or whatever. I don't care what the name is. So the first function is blue and the second function is this reddish color. And we can see clearly that these are reflections of each other about the x-axis. If I fold the paper along the x-axis, these graphs would perfectly align. So we see that this is how I reflect a function about the x-axis. Just multiply the y-coordinate by -1. And so let's notice what f of x is. F of x is x squared plus 3. Now let's look at what minus f of x is. It's minus x squared minus 3x. To multiply the function by -1, you have to multiply the whole thing by -1. So if you were to write this out, we would write it like this. Minus f of x equals, to correctly do this by hand algebraically, it's minus parentheses whatever f of x is, which in this problem was x squared plus 3x. That's how you multiply a function by -1. You have to put a parentheses around it. You're not multiplying the first term by -1. You have to multiply every term by -1. This is a key thing. This is a very common mistake. People just put a minus sign in front without the parentheses, and then it's wrong. And then if you were to simplify that, that's when you get the minus x squared and then minus 3x. All simplified out. But algebraic symbolically, it's just minus f of x. How you actually do the evaluation is right here. And you have to know how to do that by hand, because this happens a lot, where you take a function's definition and you manipulate it. We need to be comfortable doing that by hand. Okay, so we have visual evidence that to reflect a function about the x-axis, you just multiply by minus f of x. There is a way to prove this, but in this class we don't formally prove things, so we just accept this as being true. There was nothing special about x squared plus 3x. This is true for every function. Whenever you have a function, if you want to reflect it about the x-axis, just put a minus sign in front of it. And so the reflected function is minus f of x, or if you want to multiply it out by hand, in this particular problem, minus x squared minus 3x. Okay, now let's talk about how you reflect about the y-axis. So let's go back to our original function. Here are the points I plotted. If I want to reflect about the y-axis, let's say take this point right here. This point was 2 comma 10. So this point is at 2 comma 10. If I want to reflect about the y-axis, then I'm folding on the y-axis, not the x-axis. I fold on the y-axis, and so this point moves horizontally over. And what happens is the y-coordinate stays the same. The thing that changes is the x-coordinate. So instead of being at positive 2 comma 10, when I reflect, I go to minus 2 comma 10. And so a reflection about the y-axis means multiply the input value by -1. Well, the input value is called x. So if I want to multiply the input value by -1, I go f of minus x. I put the minus sign on the x. Everything else stays the same. I don't change anything else. And there we see that this is indeed reflected about the y-axis. To see it even better, I can plot both functions at the same time by putting it in braces, making that list of functions. Maybe I should change the plot range to go to +7 so you can see it even better. These functions are reflections of each other about the y-axis. If I fold the blue function about the y-axis, I will get the red function, and vice versa. Now some functions are the same. When I reflect about the y-axis, it doesn't change. So let me go ahead and change the definition of f. Let's say I had x to the fourth plus x squared. And let's plot this function just to get an idea of what it looks like. We see the output values get very large very quickly. It looks like this is, let's get the coordinates tool. This is 0, 0. This is the origin. So we don't need to change the plot range on this. Now it looks like it's the same graph. That it's if I reflect it about the y-axis, I get the same graph. So it looks like it's symmetric about the y-axis, and we can verify that by plotting the function and then its reflection about the y-axis. That's f of minus x, and we see that the two graphs are superimposed on each other. They are the same function. When this happens, we say that the function is even. When a function is already symmetric about the y-axis, it's called an even function. You notice that what this means algebraically is that f of x and f of minus x are the same thing. So watch, f of x is x squared plus minus x, and watch what f of minus x is. It's x to the it's x to the fourth plus x squared. F of minus x is x to the fourth plus x squared. The function doesn't change. Now to show this by hand, you would have to show it this way: f of minus x, f of minus x equals, and then you have to replace each instance of x with minus x. Now you have to do this correctly, and when you replace a letter with another letter or another symbol, you have to put it in parentheses so you don't make a mistake. So I'm taking that x to the fourth and replacing x with minus x. I have to put it in parentheses, otherwise my replacement is wrong. And then I put minus x, close the parentheses, and then square it. And then when I simplify this, minus x to the fourth power is just x to the fourth, because the minus sign dies out. Minus 1 to the fourth power is 1. And the same thing for the x squared. Minus 1 squared is 1. So I do get x to the fourth plus x squared. Now, if you're ever asked to prove that a function is even, this is what it means to prove that it's even. You have to show the steps. You have to replace x with minus x and show that when you do this, you end up with the original function. Typically, we'd write this horizontally, but it's too difficult to type it out horizontally. We don't like to write mathematics horizontally. We like to write it vertically. So typically, this is done vertically. We don't do it horizontally. But this is what it means to show it algebraically, to prove that this function is even. It means that when I replace the input value with the minus of the input value, the opposite of the input value, I don't change the function. I still have the same function. If you have a polynomial in which all the powers are even, that's an even function. That's what we mean by even. And that's why it's called even, because all the powers are even, then it's an even function. But there are functions that don't have anything to do with polynomials that are even functions. And when you take trigonometry, cosine, you'll do something called cosine function, and that's an even function. Algebraically, this is what it means. You're showing that f of minus x is the same thing as f of x. Well, now let's look at f of x equals x cubed plus x. And let's look at this function. And we get this this graph right here. Now this function has an interesting property. When I take this function and I reflect it about the x-axis and then reflect it about the y-axis, I'll get the same picture. And let's just see that. So when I reflect this about the x-axis, that means put minus f of x. So it's minus f. And then I want to reflect it about the y-axis, so it's minus x. So notice I had to put both minuses. The minus sign on the x means reflect about y. The minus sign in front of the f means reflect about x. And notice how the two functions, the graphs were superimposed on each other. You get the same picture. Now, when a function when it has the same graph as when you reflected about y and then x, this is called an odd function. So an odd function is a function that satisfies this algebraic property. That means that f of x, when you simplify it, is the same thing as minus f of minus x. That's what it means to be an odd function. And the way you verify that by hand is you have to evaluate what minus f of minus x is. So let me just do that real quick in this problem. So we would go minus f of minus x. That's the same thing as minus parentheses, and then I evaluate minus f of minus x. So I put in parentheses minus x cubed, and then plus parentheses minus x, and that wasn't raised to a power. And so now I simplify this. Minus x cubed is minus x, so I'm going to get minus parentheses minus x cubed, and then plus minus x is minus x. And then now when I distribute that minus sign out in front of the parentheses, I get positive x cubed plus x. And that's the same thing as f of x. So when you're proving that a function is odd, you have to show this chain of equalities. You have to show that when I take minus f of minus x, that I can algebraically manipulate that to get back to f of x. If you can't do that, then it's not an odd function. Notice that in Mathematica, f of x is that, and notice what f of minus f of minus x is. You get the same thing. So this is a mathematical way of showing that they're the same function. To do it by hand, though, you have to do what I typed up here. That's the steps to actually proving it. This is just to give you a guidance on it. Let's take a look at f of x equaling x squared plus x and see what happens. F of x is this. F of minus x is x squared minus x. It's not the same thing as f of x. So that proves that it's not an even function. And then minus f of minus x is x minus x squared. So it's minus x squared plus x. It's not the same thing as the original function. So it's not an odd function. And then graphically we can show this. We're going to go f of x minus f of minus x. This is going to show that it's not an odd function, and then show that it's not an even function. I do the f of minus x. And we see none of these are superimposed on each other. So this function is not even or odd. Most functions are neither even or odd. But some functions are even, some functions are odd. Well, let's look at a famous function that is odd, and that's the function f of x equals the cube root of x. Whoops, not the square root of 3, but the cube root of x. This function is odd because when I go minus f of minus x, I get minus cube root of minus x. Well, cube root of minus x, I can rewrite that as cube root of minus 1 times x, which is the cube root of negative 1 times the cube root of x. And the cube root of negative 1 is negative 1. And so that simplifies to the cube root of x. So what that means is that f of x equals minus f of minus x. And just to see concretely, the cube root of minus 8 is minus 2. which is the same thing as minus cube root of 8. So, or another way of putting that would be minus cube root of minus 8 is the same thing as the cube root of 8. This is how, but to show, this is, I'm just showing it for one value right here, for when the input value is 8. So to show it's odd, you have to show it for every value of it, every input value. That's what this does right here. This is algebraically showing that no matter what value you put in for x, you end up with the original function when you have minus f of minus x. Over here, I just did it for one value of x. That's 8. Doing it for one value of x proves absolutely nothing. You have to do it for every value of x. That's why you have to do it generically, which is what I boxed in right here. Well, let's go back to Mathematica, and let's see something strange. Let's go f of x right here equals x to the 1/3 power. That's cube root. Cube root is 1/3 power. And let's plot f. And we see something very odd. There is nothing for the negative values of x. Maybe you see the plot range stops at 0, so maybe there's something wrong. So we'll just go plot range to show you that it really is a bad thing on Mathematica's part. Let's go from minus 3 to 3. And we see that there is no values below the x-axis. This is an odd thing because we just showed that this is an odd function, which means that when I reflected about y and then reflected about x, I get the same picture. But if I reflect this picture about the y-axis, then it looks like this. Let me show you when I reflected about the y-axis. That's f of minus x. So when I reflected about the y-axis, I get that. And then when I reflected about the x-axis, I reflect that, I get this piece down here in the third quadrant. But the graph of f doesn't show that. Well, that's because Mathematica isn't graphing this as a real function. People who design Mathematica know a great deal of mathematics, and they're using something called complex analysis. This is a fairly advanced course. So it's not graphing cube root of x the way we expect it to graph it. It's graphing it wrong, so to speak. And so this is an annoyance. In some sense, Mathematica knows too much mathematics. But we know that this is an odd function. And so we know that when I just graph f of x, and I see this, I know it's wrong because I know that there is a piece for negative values. This is defined for negative values of x. Like f of negative 8 is minus 2. But Mathematica is not giving me that information in this graph. Well, since I know it's an odd function, I can still graph it. I just have to tell it to graph f of x, and then I tell it to graph minus f of minus x. And then it's going to give me the two pieces. These two pieces together are the graph of f. I have to do it in two pieces in Mathematica. Note that f of minus 8, watch what it gives me. It says 2 times the cube root of negative 1. So let's say I want that in numerical. So I'm going to go f of minus 8.0, give me a numerical output. And it gives me this complex number. And that doesn't look like the cube root of negative 8. But it actually is the cube root of negative 8. There are 3 cube roots of negative 8. Watch this. I'm going to cube that answer I got before. When I raise it to the third power, I get negative 8. This part right here is to the negative 15 power. It's an approximation. This part is 0. Something to the negative 15 power, it's basically 0. This is negative 8. And so Mathematica is giving you a complex answer to this. There is a real number that is the cube root of negative 8. That's negative 2. And we'll explore this more in chapter 4 or chapter 3 or later on in the class. We'll explore this concept in greater detail. But for right now, we know that that this function is not behaving the way we expect it to behave, but we can get around it. If I want to evaluate f of negative 8, then what I have to do is evaluate minus f of 8. It's negative 2. Because f of x, for an odd function, we have this important property that f of x equals, f of minus x equals minus f of x. To see that, just go back where we did this above when we talked about odd functions. So see that, just go up to here where we did these odd functions. Right here, this equation right here, just multiply both sides by minus 1, so you get minus f of x equals f of minus x. This is just another way of stating that same equation. So if I want to evaluate f of negative 8, then I just go minus f of positive 8. And so that'll work. If you want to graph it, then you need to plot both of these. You need to plot the reflection about y and then x, and then the actual function. And then those pieces, both pieces together, is the graph of f. This is only going to be a matter for us for odd powers of x. Odd powers of x, Mathematica deals with in a way that we don't really expect. But it's okay because we know that the odd powers of x are odd functions, and so we can deal with that. So this isn't going to be too major of an annoyance for us.